Are we live now?
Yes, I think so. We are live.
Okay, let me start then. Hello, everyone. Good morning. My name is Rakesh, and today I'll be presenting a brief introduction to MQSim, which is a state-of-the-art SSD simulator that is widely used in both industry and academia. So let me quickly jump to the outline for today's meeting. So today we'll be looking at a brief refresher on the internal components of a modern SSD, and these are the components which MQSim models in the simulator. And then we'll go through an introduction to MQSim. Then we'll look at how MQSim works, the mechanism of MQSim. Then we look at the code structure and how to configure MQSim to run some tests or to check the performance of the configuration that you need. So now let's look at the internal components of a modern SSD. So a modern SSD, typical SSD has two parts to it. One is the front end and the back end part. So the back end part is basically the actual flash chips or the flash packages. So these can be NAND flash memory based flash chips, or it can be PCM chips, or it can also be something like 3D point packages, which are quite new. So these memory chips are connected through a shared channel, and there can be multiple shared channels within the SSD, and a number of flash chips are connected to each shared channel. And the flash chip is, if you look at the architecture of a flash chip, then you have multiple dies in a flash chip. These dies are independent packages which can execute commands, and these are connected through a bus interface, and also each die contains two planes. Let's say two or more planes, and each plane will have blocks and pages within the blocks. So this is the back end, the components of the back end of the SSD. Now we look at the front end. So the front end has a host interface logic, or the host interface layer, which implements the protocol that is used to communicate with the host. Two popular examples are SATA and NVMe. And the host interface layer basically tries to improve the parallelism between the host and the SSD. And then we have the flash translation layer, which performs a bunch of functions and manages the resources of the SSD. It manages the mapping table, which is a very critical part of the SSD. And then it also manages some of the queues and the buffers that are there in the SSD for high performance. So these are the responsibilities of the flash translation layer. It also performs critical functions like garbage collection and wear leveling. And then we have something called the flash channel controllers, which are the components which send the commands to the actual flash chips, and also transfers data between the flash chips and the front end. So these are the components of the components of front end and the back end of the SSD. Now, what is let's look at FTL in a bit more detail. So FTL, as I said, manages the SSD's resources. And why do we need the FTL? The reason for having the FTL is that there is flash memory itself has an inherent limitation that any new write that should be performed, that should be written on a page should be preceded by an erase operation. So the flash writes can only be performed on pages that are erased. And so so every time there is an update for a logical address sent by the host, then we need to perform out of place updates, which means that we write data to a different page, and then we mark the old page where the previous data was written as invalid. And to achieve this, we have a mapping table which translates the addresses, the logical addresses to physical addresses, and this mapping table helps in maintaining the current location of the data, which is mapped to a logical address, and this mapping table is very critical to the performance of the SSD, or to even make the SSD functional. So in this case, to improve the performance, there is also a cached mapping table, which means that there is a DRAM component within the SSD, which DRAM space where this mapping table is partially stored to improve the lookup of the mapping table entries. So this is about the mapping table. So what do we do with these invalid pages? As we have discussed in some of the earlier lectures, the garbage collection process, which is a key process in SSDs, will reclaim all these invalid pages, and it does it off the critical path of latency. So it can do it in the background whenever the host operations are not being performed. So these are some of the main responsibilities of the FTL, and the FTL also has to perform the something called where leveling, which where the pages are written to different blocks, so that the age of the device is or the device is worn out uniformly. So it has to take care of that as well. So and you can see here there's also a cache management component, which is basically related to the data cache. So the DRAM is also used for to store some of the recent entries that are written or read from the flash chips. So this acts like a cache, and this also improves the performance and decreases the resource contention. Basically, the shared resources such as the channels and the chips, and so it reduces the latency. So now that we have looked at there is the front end, the back end, and all the components of the SSD. This is mostly what MQSim models in the simulator, and we'll briefly look at what and go through what the MQSim does. So MQSim can accurately model the conventional SATA-based SSDs and modern multi-queue SSDs as well. So SATA-based SSDs are SATA is a protocol which was implemented for hard disk drives, which has rotating parts, and multi-queue SSDs, mostly NVMe protocol, has become the de facto standard for high performance SSDs. So MQSim models both these protocols, and it also supports steady state behavior with preconditioning, and it also models the end-to-end IO request latency. These three things are very critical to understand the behavior of an SSD, and we look at it in a bit more detail. So the MQSim is mostly flexible in design. It has modular components, and it also has the ability to support emerging non-volatile memory technologies. A user can actually go and plug in the configuration of a 3D X-point chip, or a Samsung Z NAND, which is one of the state-of-the-art SSD for high performance. So it actually can support all these configurations. And it's also open source, and this is the GitHub link for anyone to download the code and play with it. And it's mostly written in C++, so anyone with basic knowledge of C++ can easily understand the code. So let's look at what is the support for multi-queue protocols. So a conventional host interface, which is, for example, SATA interface, was designed for magnetic hard disk drives originally, and it only supports thousands of IOPS per device, or the throughput is limited. And so in a SATA SSD, so you have, if let's say 3 processes are running in the host system, the operating system running on the host will have software IO request queues, which will take the request from these processes, and it sends it to an IO scheduler. The IO scheduler has to basically schedule these devices and send it to the device, as requests and send it to the device, and it also has to maintain the fairness among all the IO requests. So the key responsibility is on the operating system here. And we only have one request queue, which is facing the device, or through which the requests are sent from the host to the device. And this is why it happens in a serial manner. So the requests are sent in a serial manner, and the device um, will perform or process the request. So the reason for this is that this was designed for hard disk drives, where the read where a read or a write operation would take a lot of time, and that is the reason why there is a single queue, which would be enough for the performance of a hard disk drive. But this cannot work very well for a NAND flash or a state-of-the-art NAND flash memory, because the read and write latencies are much faster. So uh, to make the performance better, a few years ago, NVMe protocol was introduced, which basically introduces multiple queues. And so there are many queues for each process to use, and it takes advantage of the SSD throughput and enables millions of IOPS per device. And this also avoids the OS intervention, which means that the request can be sent directly to the device from the processes, and these request queues are hardware IO request queues. So the process would directly uh, uh, put the requests in these queues, and the SSD device can handle these queues. So we have got rid of some of the overheads of the operating system, and but the main challenge here is that the SSD must perform the scheduling and also ensure the fairness. So MQSim models these two protocols, and now let's look at what is a steady state model. So SSD should be evaluated in a steady state, which means that if the SSD is fresh out of the box, which is if the SSD is new, then it cannot perform. It's most unlikely that it performs garbage collection. So if the garbage collection is not performed, then we would not know how the performance is impacted when there is garbage collection. And also, in a new SSD device, the data cache is not warmed up, so which means that there won't be any entries in the data cache, and the request will have to go to the back end all the time, and it won't be served from the data cache. So many SSDs simulators actually simulate only fresh out of the box devices, or it incorrectly models the steady state behavior. And why is this difficult is because it's very slow. Modeling the steady state behavior is very slow, because we need to write a large amount of data to the SSD to fill the capacity of the SSD, if that is when the garbage collection gets triggered. And also some of the traces that are available in available online are not large enough for a proper warm-up of the device. So that is the reason why it's very critical to evaluate the SSD in a steady state, where garbage collection is getting triggered and data cache is also having a lot of entries. There are some workloads which actually can end up in thrashing the data cache, which is also which is also a critical behavior in which the SSD has to be evaluated. So now let's look at the complete model of request latency. And in this, we have taken a small 4K read request from the host to the backend, and we'll see how MQSim models the latency for at each stage of the request processing. So let's say a user application sends a read request for 4 kilobytes. So then the first thing that happens is it gets enqueued. The request is enqueued in the submission queue, which is there are two queues in the between the host and the device. One is called the submission queue, and there is a completion queue. So the request is put into the submission queue, and the result is when the request is processed, an entry is put into the completion queue. So there can be multiple submission queues in the device. So a user application will enqueue an IO job into the submission queue. Then the host memory will into the host memory. The submission queues are in the host memory, and then the request is sent to the host interface layer through the PCIe protocol, and then from the host interface layer, if it's a large request, it will be split into smaller requests. But here in this example, we have a 4 kilobyte request, so it will be directly sent to the SSD firmware, and the read request is transferred to the chip by the flash controller. And the flash read operation is performed in the NAND flash chip, and from there the data transfer has to happen. The read data has to be sent back to the host, and that is through the flash channel. So this is the read data is sent from the flash chip to the flash channel to the firmware through the flash channel, and from the firmware it is sent back to the host interface layer and back to the host memory. And this again is sent over the PCIe protocol. Now, any simulator has to model all the latencies of all these data transfers and command transfers. So let's see how much a 4 kilobyte request takes. So here we see that the command transfer usually takes around less than 1 microseconds. And the flash read itself, which is one of the main latency components, takes around 50 to 110 microseconds in a TLC NAND flash memory. And then we have the data transfer from the flash chip to the SSD firmware or to the FTL, which takes around 20 microseconds through the flash channel. And then the response or the data transfer from the device to the host memory takes around 4 microseconds. So these are some of the latencies that needs to be modeled by the simulator, and MQSim does that. Let's say you have a different configuration. Let's say you have a Samsung ZNAND SSD or a 3D Xpoint SSD. So the SSD, the simulator should also be able to adapt itself because the flash read in those configurations take very less time compared to what we see here. It takes around 3 microseconds for a flash read operation. And due to the high bandwidth availability in those devices, even the data transfer latency takes very less. So the simulator has to model these latencies in a correct manner. So to to model the performance of the device. So let's look at what are the different latency components that are modeled in the SSD backend. We have the address and command transfer to the memory chip. And then we also have flash memory read and write execution. So reads are typically faster, writes take a lot of time. For different NAND flash technologies, let's say 1-bit, 2-bit, and 3-bit per cell. And we also perform data transfer in case of write from the host to the flash chip, and also in case of read, we need to transfer the data back from the flash chip to the host. So these are the components that are modeled in MQSim, latency components, and these latency components are also modeled taking into account the die and plane level parallelism. So as I mentioned in the introduction slide, that a die is an independent execution unit. So if we send commands to multiple dies, it can perform the execution in parallel. And also similarly at a plane level, if you send a multi-plane command, the execution is performed in parallel across different planes within a die. So these two levels of parallelism also has to be accounted when calculating the latency. And also there are other advanced command execution modes, such as multi-plane operations, as I said, and also copy back operations, where we actually don't transfer the data back to the host itself, and it's kept in the buffers within the device and then moved back to the flash chip. So some of these advanced command executions also have to be taken care. And there is also a cache read command, cache read and cache program commands, which needs to be modeled as well. So these are some of the latency components, and the simulator also needs to be aware of the size of the read and write operations. Write operations are typically performed in a page-sized manner. So if the SSD supports around 16 bytes of size, page size, we need to always write the write operation should always be performed in the page size. But read operations can be performed at a sub-page granularity. So it can be performed at 4 kilobytes, 8 kilobytes, or 16 kilobytes. So the SSD simulator should be aware of the sizes of the read and write operations. So these are some of the parameters that the SSD simulator should be aware of while modeling the latency at the back end. But at the front end, as I said, we have NVMe multi-queue and SATA native command queue models for a modern SSD. So SATA native command is basically at the operating system level, the SATA protocol, basically the operating system decides on what is the priority of different requests, or basically to enable fairness, the operating system decides which requests have to be scheduled first, and so on. So these things are modeled in the MQSim. And for NVMe protocol, MQSim models different priority classes. I think there are 4 priority classes currently in MQSim: urgent, high, medium, and low for the host side request queue. So we can assign different priorities for different queues, and based on the priority, the requests are processed in the order of the priority. And we also have a data cache manager, which is a DRAM based cache, like we saw in the introduction slide, which uses a least recently used replacement policy to cache recently accessed data. And we also have different FTL components modeled in MQSim, such as address translation unit, garbage collection, ware leveling, transaction scheduling unit, and support for multi-flow request processing. So these are some of the components which are modeled in MQSim, and for more comparison with other simulators and more details on each of these components, I would encourage you to read the paper. And it's a nicely written paper with a lot of results and sensitivity analysis. So please take a look. So this marks the introduction to MQSim, and I've tried to give a good, picture of what is going on and behind the scenes. So if you have any questions now, we can discuss. Else, I'll move on to the next section. Okay, so next I'll move on to the mechanism of the simulator. So in the mechanism, MQSim is a discrete event-based simulator, which means that each operation performed by MQSim is an event. Let's say the command address transfer or the read data out that we discussed. These operations are considered an event, and they are performed at discrete times. So what do I mean by discrete time? So there is a red black tree that maintains the events in the order of their completion times. So each node in the red black tree has a key which indicates the timestamp of the event when it finishes, and also the value is the callback function. So when the event finishes, or when the event is supposed to finish, a callback function is called, which marks the end of the event. So for example, at time 5, a data transfer event starts, and the event will execute for another 5 time units. So the simulator will insert a node with 5 plus 5 as the key and a callback function into the tree. So at each simulation cycle, the simulator will try to find the smallest time which has to be, or the event which has the smallest time from at that point to execute, and it will set the timer to that timestamp and execute the callback function. So the simulation engine works like this, and MQSim can support real disk traces from sources like MSR, Cambridge, block IO traces, or YCSB, and also it can generate its own traces, which is called synthetic workloads. So this is the mechanism of the basic mechanism of the simulation engine. Now we look at the initialization of MQSim. So MQSim components like FTL or the SSD device or the transaction scheduling unit are represented as objects and are maintained in the map. So these objects in the map are iterated through and corresponding functions are executed. So each object maintains their own version of different interfaces which are required for the simulator to call the objects. So we need to have we need to actually implement interfaces like setup triggers, start simulation, which is called by the simulation engine. So if you look at this figure, you will see that there is a setup triggers function which is getting called. So when the simulator is getting initialized, it goes through all the objects that are there in the map, and then it will call setup triggers. What does setup triggers do? It will basically look at the nature of the object, and it will basically see if there is any notification or a trigger that needs to be set up for that object. And there is also a validate simulation config, which is where it goes through all the objects again in the map, and then it will validate whether the configuration of that particular object, let's say the SSD device, is correct. So that is about validate simulation config, and then it will also go through um, the different objects, and it will execute the start simulation. So that is the entry point for all these objects. So in start simulation, we have a while loop, which will look at the arbitrary that I just mentioned before, and it will try to get the different nodes from the arbitrary, and it will get the the node with the least timestamp, and it will use that node to fire the event. And to fire the event, it uses the execute simulator event interface, and with that object. And then once it calls that simulation event, it then deletes the event, because it's already triggered the event. So it deletes that event from the arbitrary. So this is the basic idea of a start simulation function. And the callback function is execute simulator event. So we need to define the callback function for each of these nodes or each of these commands that we command or data events that we insert into the arbitrary. So how do we, now that we have looked at how to initialize the MQSim and how to start the let's say the simulation, now we'll look at how to add an event into the arbitrary. So a simulator event is registered using register sim event function. So in the register sim event function, it basically calls a constructor called sim event with all the different parameters such as fire time, target object parameters, and type. And then it inserts this event to the arbitrary, which is called event list here. So an event is registered, let's say, for sending a read command and command and address. So we basically call the register event sim event, and we give the time, the current simulator time plus suspend time plus the read command time. So this is the timestamp for the event to get executed. And then we call the callback, the macro which is used in the callback function. So read command address transferred will be the macro which is looked up in that callback function, and then the routine is executed. So this is how we register an event in the MQSim. So this kind of gives an idea of how what are the key functions that needs to be invoked in the MQSim, and how do we, let's say, initialize this engine, how do we start the simulation, and how do we register an event. So tomorrow, if we are adding a new component into the MQSim, we need to stick to these kind of these interfaces, and then use this register sim event to add an event. So next, if you have any questions, we can discuss now, or else I'll move to the code structure and look at how MQSim, the code structure in MQSim looks like, and what are the different files that we need to look at. So any questions so far? Okay. So let's look at the code structure. So MQSim has a bunch of files and folders. If you take a dump of the GitHub code repository, So you have some things like some of the main folders that we need to look at is are basically the source folder, the traces folder, and also files like SSD config.xml and workload.xml. So SSD config.xml is basically a configuration file that that is used to define the preferred SSD configuration. You can input parameters related to a TLC NAND device, or a 3D point device, or a Samsung ZNAND device in that XML. Then there is a workload.xml which defines the workload parameters, and we'll look at these two configuration files in a bit more detail in the next few slides. So then we have the traces folder, which is where the traces are kept. If we need to have use a trace based workload, and then we have the source folder where you have a bunch of folders inside that. Let's say the sim folder is contains files related to the simulation engine. The NVM chip folder contains code related to the NVM chip, mostly related to the back end of the SSD, and it contains files for die, plane, block, and page. And the SSD folder inside the source folder contains files related to the flash translation layer and the transaction scheduling unit. And the host folder contains files related to the trace based workload generation and synthetic workload generation, and also the PCIe protocol, which connects the host to the SSD. Now let's look at the code flow. So for any request, it has to be the request has to come from the host, and then a data cache. If there is a let's say if it's a read or a write, whether the data is available in the cache, and then it looks at the address translation unit to see if there is a mapping entry in the address logical to physical mapping table. If it's not there, then a new entry has to be added. Then it goes to the transaction scheduling unit, which basically schedules the events to different channels and chips in the backend. And it is sent through the flash controller, and it goes to the NVM chip. So this is a flow. This is the flow from the front end to the back end. And some of the important functions that we need to look at are for the data cache manager, we need to look at process new user requests. And for the address mapping unit, we need to look at translate LPA to PPA and dispatch function. And for the transaction scheduling unit, you need to look at schedule function. And from the flash controller, we need to see the send command to chip function for understanding how the code works in each of these components. So so this is about the code structure. I'm sure there is a lot of code there to understand and read, but this is just a brief introduction into what are the important functions that we need to look at and how the code, the execution flow works. So next I'll go into how we configure the MQSim. And so let's look at the SSD config.xml, which is a file which we use to define the preferred SSD configuration. And we have the host parameters. So we can define the PCIe lane bandwidth, which is the external IO bandwidth of each lane between the device and the host. And this we can define in terms of gigabytes per second. And then we have the lane count. So usually PCIe Gen 4 has around 4 lanes. So we can define the number of lanes through which the data is moved from the device to the host. Then we have device parameters such as host interface type, which is the type of host protocol that is implemented in the HIL, which is NVMe or SATA. And we have the IO queue depth, which is the length of the host side queue. So in NVMe, we have multiple such queues which can take requests and parallelly execute them. So we need to define the length of the host side queue. And we also have the data cache capacity, which is the size of the DRAM data cache in terms of bytes. Then we have something called the ideal mapping table. So, as I mentioned earlier, we have a cached mapping table to store some of the entries of the logical to physical address translation in the DRAM cache. But let's say if we want all the entries to be cached in the DRAM, then we set the ideal mapping table to be true, which actually stores all the entries in the DRAM. This is not the case in a real SSD, but we can do this for checking the ideal performance. Otherwise, the SSD only stores a part of the entry into the in the DRAM, and which is defined by the cached mapping table size. And if there is any entry missing in the cached mapping table, then it has to go to the backend to fetch the mapping table entry. Then we have the transaction scheduling policy, which is the scheduling policy to send the request to the backend. And there are multiple policies that are already supported out of the box in the simulation, in the simulator. One is called the out of order, which is based on a prior work. And then we have priority out of order transaction scheduling policy. And this implements out of order policy with NVMe priorities. So as I said, the NVMe has 4 priorities for different queues, like urgent, medium, high, and low. So these are some of the components of the device. And if you look at the backend configuration, we have the flash channel count, how many flash channels are present in the device, and the flash channel width, which is the bandwidth of each flash channel, and the chip number per channel. So how many chips are connected to each channel in the SSD backend. And in terms of NAND parameters, we have we can support different flash technologies. We can support SLC, MLC, and TLC flash cells, and also the page read latency for LSB, CSB, and MSB in case of a TLC page, TLC word line. We can define different read latencies for these pages. And also we can have page program latency, the block erase latency, and we can also define the endurance of the block by defining the P limit of the program erase cycle limit of each flash block. So then we have some more parameters like how many dies are there per chip, the number of planes per die, the number of blocks per plane, and the number of pages per block. And we also have the page capacity, the metadata capacity. What is metadata capacity is that in every page there is a small area of the page which stores the metadata, like the logical to physical address, the logical address of the page, and also a signature, and many things that are required by the FTL to identify the page. So this is stored in a small area within the page called metadata. And so these are some of the key parameters that are required in the SSD configuration file. So any user who wants to use the simulator has to define all these parameters. There are some default file configurations that are already provided in the GitHub. which you can also utilize. Then we look at the workload configuration. So as I mentioned, there are two types of workload that we can use in this with the simulator. One is a trace-based workload, where we can define an IO scenario within this XML file, the workload.xml, which defines a trace-based workload configuration. So this has many parameters which will define the workload that we use in the experiments. So let's say if we set the channel IDs to 8 channels, then the workload will the request in the trace will be sent to all the 8 channels, and the number of chip IDs will define how many chips are being used by the workload. And die IDs and plane IDs also define something similar. And then we have the initial occupancy percentage, which will define how much of the device is already occupied with data. And the file path will define the trace file, which is used for generating the request. And then what percentage of the trace needs to be executed, and the time unit, whether it's nanoseconds, microseconds, or milliseconds, can be defined here. And we can also define the priority class for the NVMe queues and the device level data caching. So these are some of the parameters that are required for a trace-based workload configuration. Then we have a synthetic workload configuration, which is basically configuring the simulator to generate its own request or the workload. So in this, we again need to add an entry into the XML file, something like IO flow parameters set synthetic, which will define the synthetic workload. And we have similar entries like the trace-based workload for synthetic workload as well. But it also generates, since it generates its own requests, we need to define the address distribution, and the queue depth for basically whether the workload has to be generated based on the queue depth or something else. Then how much of the workload should be reads and as opposed to writes, and what is whether the addresses that are generated, they should be aligned, they are aligned to some granularity, or it can generate unaligned addresses. So if it is true, then we need to set the address alignment unit, which is in terms of sectors, which is 512 bytes typically. And so here it's set to, let's say, 8K. And the request size distribution is fixed. What is the average request size that needs to be generated? So these are some of the parameters, and I would refer you to the README file in the GitHub repository, which has a lot of information on all these different parameters that are used for generating the workload. So, so we have looked at trace-based workload and also the synthetic workload. Now, when we run the simulator, we will get an output file, which also gives a lot of information. And we need to basically look at all these different the numbers that it generates, and that can be used for our analysis. So I have only shown a part of the output file here. So let's say only the host, the parameters related to the host. So we see the trace file that was used for generating the workload, and we see how many requests have been were processed, and within those requests, how many of them were read and write, and so on. And we also look at the throughput in terms of IOPS. the read throughput and the write throughput, and how many bytes are transferred to the device from the request, and how many of them are read and write, and the bandwidth of the device, the overall bandwidth, and the response times. So these are some of the important things to quickly look at how our simulator is running, and also if we have made any changes in the simulator, we need to look at these values to understand if we have improved the performance, or we need to investigate further. So these are this is about the host related parameters, but if you look at the actual output file, then we will have a lot of entries related to the device, and also the different queues that are there in the flash translation layer. So it will give a lot of data which can be useful in analyzing the performance. So finally, we look at how we use the MQSim. And if you are a Linux user, then we just download the code from the GitHub, and then we run make. And if we have to run the simulator, then we basically pass the SSD configuration file and the workload definition file in this format, and that will run the simulator. If you are in the Windows ecosystem, then you can open the solution file that is provided in the code, and set it to release or debug, and then compile the solution, and we can specify the paths within the Visual Studio environment. So so that is about the Windows ecosystem. So this is kind of a brief introduction of MQSim. I would encourage everyone to download the code and play with it. And if you have any questions, please feel free to ask me or anyone else in the or Mohammed in the group, and we'll be happy to help. Yeah, so that's the end of my presentation. Do we have any questions? Okay. So if there are no questions, then yeah, we are done for today. Let me stop the live stream now.